Okay. So this next is we want to know how we can do the DC analysis of the bias circuit. DC analysis of the bias circuit. So the objective of this analysis is we want to determine the Q point of the transistor with a certain circuit configuration. Okay. So let's say you are given the amplifier circuit. So a complete amplifier circuit will have a connection. So you have this amplifier circuit. So the complete circuit of amplifier may have connection to the source, and will also have connection to the load at the output. Okay, so the connection between the source and to the amplifier and amplifier to the load, sometimes we use the capacitive coupling. We couple it with the capacitor. So for DC analysis, you need to replace the capacitor with open circuit. So this is the first step. The second step is after you remove the capacitors, you identify the type of the circuit configuration. If the circuit configuration is voltage divider, you need to simplify the circuit using the Thevenin equivalent circuit. So this step also similar to the BJT procedure. So after that, the third step is write down the current equation of the transfer characteristic. So the third step is it's not related to the circuit, but you need to write down the transfer characteristic IDF as a function of VGS. So this is ID equal to K VGS minus VGS TH square. So this is the equation that you need to write down. So in this equation, there are two constants that you need to identify. The first is the K value and the second one is VGS TH. Okay, the next step is you do the KVL at the gate terminal loop, or we call it the input loop. So when you do the KVL, make sure that you consider the gate current is equal to 0 and ID equal to IS. So in this step, you will have two equations. So the first equation is the transfer characteristic, and the second equation is the derivation of the KVL. So at the next step, you can solve the ID and VGS by solving the equation from this step 3 and the step 4. Okay, remember the step 3 is the equation of transfer characteristic. Step 4 is equation from the KVL and the input loop. Okay, this number 5. So for the number 5, you are solving two equations. So the solving of equation can be done two ways. The first way is by using a mathematical calculation, and the second way is using the graphical. So from this mathematical and graphical, you can get the solution, and then you can expect two solutions from this two equation, because this is a quadratic, because the transfer characteristic is a quadratic equation. So you have the two possible solution. So the valid solution should be where the VGSQ is above the VGS-TH. So you need to make sure that your solution is above the threshold voltage, because if the solution is below the threshold voltage, this is the condition of transistor is off. So you need to make sure this. Okay, after you settle, you finish calculating the IDSQ and VGSQ, you can calculate the VDSQ from the KVL at the output loop, or we call it a drain source loop. Okay, let's go to the first example. So this is the fixed bias circuit. Okay, so this is fixed bias circuit. There is no capacitor, so no need to remove the capacitor. And then this is not voltage divider, no need to do the circuit transformation. So the next step is write down the transfer equation. So the transfer equation is ID equal to K VGS minus VGSTH square. So K is 0.15 milli, VGSTH is 5 volt, so you get the equation is ID equal to 0.15 milli. This is VGS minus 5 square. So this is your first equation. Okay, and then the next step is you do the KVL at the input loop. Okay, so for the KVL at the input loop, the loop will be clockwise because, as I mentioned, the common direction for the current, drain current and source current is in this direction. This is ID. Okay, so you write down the KVL. It is minus 10 plus IG 50K. Okay, in between of the terminal, there will be always a voltage drop. So this is gate and source. So we have the drop of VGS. And then this is ID 1K equal to 0. Okay, so for the 1K, the current here is ID. I put it ID, not IS. Although this is connected at the source drain because the current at the source is equal to current at the drain. Okay, and then you know that IG is equal to 0. So this term is also equal to 0. So you have this is minus 10 plus VGS plus ID 1K equal to 0. So this is your KVL. Okay, so when you next is you have the two equation. This is the first equation, transfer equation. The second equation is the KVL. So you need to do the solution for these two equations to get the ID and VGS. So let's first use the graphical. So graphical method require you to draw these two equations. Okay. The second equation is a linear graph. Okay. So to draw, you need to have a point. Okay, you need to have the point. So let's say I put it. This is the table to calculate the point. Okay, if VGS is 0, based on this equation, the ID will become 10 milliampere. If ID is 0, the VGS will become 10 volt. Okay, so this is from this equation, you have the maximum drain current is 10 milli and maximum gate current is gate voltage is 10 volt. So, and then next we do the table for the first equation. So this transfer equation, the drain current of the transistor will become 0 when VGS is below than VGS TH. And then the ID current will equal to K VGS minus VGS TH when VGS is larger than VGS TH. So when we do the plotting, this is VGS and this is ID. So you need to start from the point above the threshold voltage. So this is 5. So let's start with the 6. And then the maximum we put it 10. So we have the 6, 8 and 10 volt. Okay. So for VGS is 6. So you insert the 6 here. 6 minus 5 is 1. 1 square is 1. So you get 0.15 milli. So and then for the 8, 8 minus 5 is 3. 3 square is 9. So 9 times 0.15 milli is equal to 1.35 milli. And then the next calculation, you do the same calculation. This is your table. So now you have a required point to draw the graph. So next let's do the graph. So the graph will be ID versus VGS. Okay, ID versus VGS. Oh, sorry. So let's this is the y-axis here is ID in milliampere, and then we have here this is VGS volt. Okay, so let's say I put here this is 2 1 2 3 4 4 1 2 3 4 8 1 2 3 4, this is 10. Okay, and then from the previous slide is the maximum current is 10 milli. So we will plot the 10 milli here. This is 1 2 3 4. This is 2 1 2 3 4 4 1 2 3 4 6 1 2 3 4. This is 8 2 4 6 8, and 1 2 3 4. This is 10. Okay, you have label, and then you label the axis. So next you can draw these two equations. So the first equation and the second equation, the first point is when VGS is 0, ID is 10 milli. When ID is 0, VGS is 10. So when ID is 0, VGS is 10. When VGS is 0, the ID is 10 milli. So you have this. Okay, so this is your KVL. So next you do the plotting for the first equation, which is the transfer equation. So threshold voltage is 5. Okay, below than 5, the current is 0 because there is no channel form inside this. ID is equal to 0 below than 5. Above the 5, there will be a current. Okay, so okay, 5 should be, this is 6 4 6. Oh, I made a mistake here. So let me correct this one. Okay, should be 1. This is 2 1 2 3 4 1 2 3 4. This is 6. This 1 2 3 4. This is 8, and oh sorry, this is 4 6 1 2 3 4. This is 8, and 1 2 3 4. This is 10. So the KVL will be this is your KVL. Okay, for transfer characteristic, this is the point of 5. Below than 5, the current is 0. Okay, and then at 6, the current is 0.15. So it's quite very low. So 6, the current is 0.15. This is 1. Okay, I put here something. This 1. Put something here. And when the voltage is VGS is 8, this is 1.35. So at the 8, this is 1. This is 1. 1.35 is around here. And at 10, the ID is 3.75. So this is 10. This is 3.75. So you draw this transfer curve, and you got this is your transfer curve. Okay. When you draw these two graph, identify the intersecting point the intersecting point will be your solution. So here the intersect is IDQ is equal to 1.5 milliampere. And then VGSQ is equal to this is equal to around 8.25 volt. So this is the solution using the graphical. Okay, if we want to do the mathematical solution, so we start from listing these two, write down these two equations. The first transfer equation is 0 ID is equal to, okay, this is the first equation, and then the second equation is minus 10 plus VGS, and then plus ID 1K equal to 0. This is the second equation from the KVL. So you solve this equation. Okay, the first you need to I recommend you to combine the first and the second equation, and then at the end you will have a equation with a VGS, okay, as a function of VGS. So from this second equation you can express what is ID. ID is 10 minus VGS over 1K. This is 2A. And then 2A you insert to the first equation. You will get 10 minus VGS 1K is equal to 0.15 milli VGS minus 5 square. So this is 10 minus VGS 0.15 . Okay, now you see we will have a quadratic equation. So you do all this calculation, you will get the equation of so this is your equation. So when you do from this equation, you solve this equation, you will get two solutions. So the VGS will be 8.33 or minus 5 volt. So you have two solutions. Because this is quadratic, so you have two solutions. So which one will be the valid solution? Valid solution is where the VGS is larger than VGSTH. So VGSTH is 5, so the valid solution is 8.33 volt. So the VGSQ is equal to 8.33 volt. Okay, so when you know the VGSQ, you can calculate the IDQ is equal to 10 minus 8.33 over 1K. You will get 1.67 milliampere. So this is the exact analysis using the mathematical. So if you compare with the graphical, so the graphical you get the VGSQ is 8.25, the IDQ is 1.5 milliampere. So it's not far, it's not close, but it's not that far. So this the solution is accepted, can be accepted.